Hello students, let's start the last part of our chapter oscillation, a very interesting concept, damped oscillation. Now what are damped oscillation? Let us understand through an example. So consider a simple pendulum oscillating about its mean position in air. That means the medium is air, a very practical situation. So as you can see, the pendulum is vibrating and the medium is air. Now my question to you students, will the pendulum move to and fro forever? That means will it vibrate forever continuously? The answer is no. We very well know in our practical life this pendulum does not vibrate forever. Now why? Why does this happen? So let's understand it. So as the pendulum moves forward, students, you can very clearly see the air opposing the motion by exerting something called as drag force. Students, this concept we have learned in 11th standard. Whenever there is a motion of an object through a medium, the medium opposes the motion by exerting something called as viscous force or viscous drag or as drag force. So in this case also, as the bob of the pendulum moves through air, air exerts drag force on the pendulum. Also, there is friction at the support which opposes the motion of the bob of the pendulum. That means, to conclude, the motion of the bob is opposed by some frictional force or drag force. Now students, if the bob has to move forward, it has to do work against these opposing forces. And for doing this work, energy of the bob is utilized. Now, these damping forces, being non-conservative forces, work done against them is never stored but rather dissipated in the medium itself. Hence, what happens? Energy of the pendulum goes on decreasing gradually or energy dissipates gradually. As we learned in energy in SHM, energy is directly proportional to square of the amplitude. If energy decreases, amplitude also decreases. Hence, amplitude goes on decreasing. Students, and finally the pendulum stops. You can check it here. Let's see in this diagram. The pendulum is pulled aside and released. You can very clearly see. We have also marked the extreme position. Kindly note the motion of the pendulum. You can very clearly see as the pendulum is vibrating, the amplitude of the pendulum goes on decreasing and very finally the pendulum stops after some time. So we saw in this case very clearly the amplitude decreases with time gradually. Such vibrations or oscillations are called as damped oscillation. So let's define periodic oscillation of gradually decreasing amplitude are called as damped harmonic oscillation, and the corresponding oscillator is called as damped harmonic oscillator. So students, to conclude, the oscillations in which amplitude decreases with time are called as damped oscillation, and in oscillations in which amplitude does not decrease, that means remains constant, are called as undamped oscillation. Whatever we have studied previous to this module is nothing but undamped oscillation, and all those formulas are also corresponding to undamped oscillation. Now let's check examples of damped oscillation. The first example that we already saw is the oscillation of the bob of a simple pendulum in air or any other medium is an example of damped oscillation. If the same bob is suspended in an evacuated chamber, that means if there is no medium, then it performs undamped oscillation. Likewise, second example, the oscillation of a stretch string in air or any other medium is also an example of damped oscillation. We see very clearly if we pluck the string of a guitar and release, the vibrations stop. After some time, it's an example of damped oscillation. The third example, very much present in our physics lab, the oscillation of a vibrating tuning fork in air is also an example of damped oscillation as the vibration stops after some time. It's an example of damped oscillation. Now, students, whichever example you take, there has to be a damping force. Now, what is the formula for damping force? Let's check it out. So as we saw, as the pendulum vibrates, there is a damping force. This damping force is directly proportional to the velocity of the oscillator. Therefore, I can write damping force is proportional to minus V, where minus sign indicates that the damping force Fd is in a direction opposite to that of velocity. In order to remove that proportionality, let's introduce a constant, and the formula becomes Fd is equal to, damping force is equal to minus P into V, where P is a constant called as damping constant. Let's find its SI unit. So damping force B is Fd upon V, force is m into A upon V. Let's write the respective units. So the unit of mass is kg, unit of acceleration is meter per second square, upon the unit of velocity is meter per second. We'll cancel meter, we'll cancel 1 second, and what remains is kg per second. So SI unit of damping force is kg per second, and the dimensions will be m raised to 1, L raised to 0, T raised to minus 1. So in this module, we learned what is damped oscillation and the formula for damping force. That's all in this module, students. See you in the next module.